Yay, we get to do some more analytical limits. So today what we're looking at is some different kinds of limits. This says the limit as x goes to 1 of this function. Well, let's see what happens if we plugged it in. 1 cubed minus 1 over 1 minus 1. We get 0 over 0. Oh no, that would be undefined. And we can't work with this. And remember, that's not exactly how we calculate the limit. If it gets 0 as our denominator, we know that that's not actually our limit necessarily. And so we need to look at some other methods. One other method is that we can actually factor out by dividing, by factoring and dividing out like factors. So this we could actually do long division too. So this would actually be plus 0x squared plus 0x minus 1. So I'm just writing out the function there. I get x minus 1. I could actually divide this out and figure out, okay, I need 2 x's here, so I'm going to get x cubed minus x squared. And so I subtract these. This cancels out. I get x squared plus 0x minus 1. So now I know I need another x here for that to cancel out. I get x squared minus x, and I subtract these. This cancels out. I get 0x plus x is x. Then I get x minus 1. So if I just say plus 1, I'm going to get x minus 1. I subtract them, and they cancel out. So this would be what's left over. So if I take out that x minus 1, I have x squared plus x plus 1 left over, and x minus 1 left on the bottom. So these cancel out. I plug in 1 now to my limit. 1 squared plus 1 plus 1. And some of you may have been able to recognize, okay, how to factor a cubic one. If you weren't, you could have done the long division, but if you knew how to do that faster, more power to you. Jump straight to that. And we solved for our limit being 3. So you want to recognize the ones that can be evaluated by direct substitution, like the ones that we did yesterday, because if so, then that's a lot faster. But if not, one method is to be able to divide it. In this case, same problem. If we plug in -3, we're going to get 0 on the denominator, so we cannot do direct substitution. But this one can be factored. What's going to multiply to give -6 and add to give 1? 3 and -2. And so now I can cancel these off because really what's happening is this is a hole in our graph, right? And that's why it's not defined at that point. But the limit is still approaching that point, even though there's a hole there. So we're canceling this off because there's a hole, there's an asymptote there. However, if we plug in -3 into this equation, we get -5. And so we know that that's still what the limit is approaching, even though there's the hole in the graph. That's kind of the point to limits. Get it? The point. Okay. Next, find the limit. The limit as x goes to 0 of this funky thing. So this one is, if we plug in 0, we're going to get 0. We cannot factor anything. And so this would be our rationalizing technique. With rationalizing, what we're going to do is we're going to rationalize our fraction. So instead of -1, we're going to multiply by +1. And whatever we do to the bottom, we do to the top. So what I'm going to do is I'm going to FOIL this. So the square root of x plus 1 times the square root of x plus 1 is just going to be x plus 1. I have a negative and a positive, so those cancel each other out. And then I have -1 times 1 is -1. All over the denominator, x times the square root of x plus 1 plus 1. Well, 1 minus 1 is 0, so that just goes away. So this is x over x times the square root of x plus 1 plus 1. And now I have an x and an x on the numerator and the denominator that can cancel off. There's my whole. So 1 over square root of x plus 1 plus 1, and I can actually plug in 0 straight into this. 1 over the square root of 0 plus 1 would be 1 over the square root of 1 plus 1. The square root of 1 is 1, so this would be 1/2. So one other theorem that we want to look at is called the squeeze theorem. So this is saying that if we have two functions, g and h, and there's a function that stays in between them the whole time, if we know the limit of h and we know the limit of g, it's saying that if the limit of h is equal to L and the limit of G is equal to L, if F is in between them, then that limit would also be L. So like at any point here where we're reaching each other, they're going to be equal because that function is in between. So if there's a function in between those outside functions, the limits are going to be equal if the outside functions limits are equal. If you're interested in the proof of those theorems, you can look at Appendix A in our textbook to get a little proofy if you want to get fun there. Okay, 2 special trig limits. And again, you can look at the text if you want to see the proof as to why these exist. But the limit as x goes to 0 of sine x over x equals 1. This we need to make sure that we have memorized. Anytime you see sine x over x and a limit going to 0, it's going to equal 1. And anytime you see 1 minus cosine x over x, it's going to equal 0, as long as the limits are going to 0. So kind of like your trig identities, this is something that you just have to know and to be able to manipulate. So we're asked for the limit of tangent x over x. If we did direct substitution, this would go straight to 0, which we cannot do. So we got to mix around with it. We know tangent x is the same thing as sine x over cosine x, right? That's the definition of tangent. And so now if I want to get this x out of the denominator, I multiply by the reciprocal, and I'm going to have sine x times 1 over cosine x times x. Because these are all multiplying, I could rearrange them. X times cosine x. And now I have actually my identity. Sine x over x is actually 1. And so this becomes 1 times 1 over cosine x, which is just 1 over cosine x. And now I'm looking for the limit as x goes to 0 of 1 over cosine x. What happens if I substitute that in now? What's 1 of cosine of 0? Well, let's look at our unit circle. At 0, we're at the point 1, 0, cosine, sine. So that would actually be 1. So this would be 1 over 1, which is 1, because cosine of 0 is 1. We're done with that one. It's just kind of rearranging to manipulate our limits to do what we want them to do. Next one. The limit as x goes to 0 of sine of 4x over x. If we plugged 0, we would get our indeterminate form of 0 over 0 because the denominator is 0 there. And so we kind of need to just look at this one and to see what we could do to simplify this. One thing that we can do is to actually go ahead and just multiply and divide by 4. So we're multiplying by 4 over 4. And let's see what happens. So if we multiply by 4 over 4, we get 4 sine of 4x over 4x. This guy can be pulled out front, the limit as x goes to 0, because it's a coefficient, and we can totally do that. We multiplied by 4 over 4 because we can multiply anything by anything over itself. This is the same thing as sine x over x. Because 4x, we could substitute that with y if we wanted to. You don't have to actually write this part out. But that would be y over y, because 4x is equal to y. You wouldn't have to actually write out this step because these are the same. We know that it goes to 1. And so we would actually have 4 times 1 because this whole limit goes to 1. And so we therefore are at 4. Okay, last one that I want to talk about. This one asks for the limit of this, where f of x is 4x minus 3. And so for this one, we actually have to plug in x plus delta x in for our x, because it's saying the f of x plus delta x. So we're going to plug that in for x. So we go 4 times x plus delta x minus 3, because that's the rest of our function, minus f of x is 4x minus 3. So this first one is x plus delta x, and the second one is f of x all over delta x. Now we're just doing basic algebra. We just got to rearrange this. So we're going to distribute 4x plus 4 delta x minus 3 minus, distribute the negative, 4x plus 3. 4x minus 4x goes away. Negative 3 plus 3 goes away. And we have 4 delta x over delta x. Well, what's delta x over delta x? 1. So we just have 4 left because those canceled off. If we were not able to cancel off a delta x, we would have had to substitute in 0. If we substituted 0 in right directly, it wouldn't have worked because we would have been dividing by 0. So this one we just had to kind of manipulate it around. Be starting to get familiar with this because as we get further into calculus, you're going to see this formula more and more. So just make sure that you're familiar with plugging in that x plus delta x in for x for those points. Thanks so much, guys.